Prompt injection threat modeling helps teams see where attackers can talk to your model and what those paths can do. In practice, it answers a simple question: which inputs matter most, and where should we spend our control budget? Success looks like fewer surprise breaches and a clear list of actions your ops team can implement in days instead of guessing. You'll walk away with a setup that maps prompt injection paths and aligns filters, tool locks, and review steps. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Prompt injection threat modeling helps teams see where attackers can talk to your model and what those paths can do. In practice, it answers a simple question: which inputs matter most, and where should we spend our control budget? Success looks like fewer surprise breaches and a clear list of actions your ops team can implement in days instead of guessing. At a high level, the idea is to list every channel your model reads, then assign a simple exposure weight to each channel. Finally, combine those weights with scenario impact and likelihood. That gives you ranked risks you can act on, and it points to controls with known latency costs. We will build a small threat model that goes from visible channels to a guardrail plan and then to a residual risk map you can monitor. This keeps the example focused and practical, so the code feels like a checklist you can adapt. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we map channels and their exposure, so we know the obvious weak spots. This snippet maps the core prompt channels and highlights which ones breach exposure thresholds. It gives you a quick inventory tied to signal. System prompt barely moves the needle, while retrieval doc and tool result show up with higher latent risk. The inline data makes the trade-offs visible at a glance. The list comprehension that produces high exposure tells you exactly which channels to gate first, and the printed output confirms the immediate shortlist for first wave guardrails. That high exposure list shows where direct attacks can land. So next, we score direct scenarios against those surfaces. This example scores your direct injection cases by turning impact, likelihood, and surface exposure into one priority number. The code keeps each scenario name linked to the surfaces you're monitoring already labels. And risk scores simply multiplies impact and likelihood by the corresponding surface exposure. So low exposure system prompt drops and user prompt or tool result rise. Pulling top direct gives you the highest product scenario to prioritize. And the printed tuple shows which direct attack should get the strongest filters right now. Direct scoring is important, but many real breaches are indirect. We need a way to trace multi-hop paths that end up at a sensitive policy. This code analyzes indirect attack paths by summing exposures along each hop toward a sensitive policy target. By listing routes that feed deployment policy, memory legs, system legs, retrieval chains, the paths array shows how a seemingly safe source can relay risk. The EXP map lookup reuses the surface exposure weights, and exposure sum converts each route into a comparable risk mass, even when a hop like memory note lacks a direct score. Top, indirect, then surfaces whichever origin path most strongly points at deployment policy. And the printed tuple flags the multi-hop vector you should coordinate with retrieval boundaries or tool permissions. With the top direct and indirect vectors identified, we translate them into concrete controls and estimate latency impact so trade-offs become visible. This snippet translates the top direct and indirect vectors into a concrete guardrail plan with latency costs. The control lookup ties each surface to the exact mix of input filter, retrieval boundary, tool permissions, or human review you already operate, so you avoid buying irrelevant controls. As the loop walks top direct and top indirect, it builds labels and sums cost from the chosen combos, keeping both the selected actions and the latency impact your SLOs care about. Printing the latency dictionary gives an instant sense of how expensive the current guardrail stack is, so you can balance safeguards against your budget envelope. Finally, we need to know what remains after we apply these controls, so monitoring and triage focus on the right signals. This example rolls everything into a residual risk grid so you know what to monitor after controls deploy. The rows list pairs raw scenarios with their assigned guardrails, which prevents teams from forgetting why a channel got review or permissions limits. The guard variable folds in the indirect route, so plan map coverage reaches past user-facing prompts into documents or tool returns that could still punch through. The ordered list and summary string turn those rows into a readable name-to-score string, and the printout shows which actors remain hottest after mitigation for faster incident triage. If you move this model into a real project, map the same names to your telemetry fields. Use your alerting to count exposures per surface, and wire the residual grid to your incident playbook. That keeps your threat model tied to real traffic instead of drifting into a forgotten spreadsheet. Quick recap. This produces a ranked threat model that joins channel exposure to scenario impact and path length. Use it before adding filtering or costly human review, and whenever you add a new retrieval source or tool. One caveat: exposure scores are only as good as the telemetry feeding them, so validate those weights with samples. Next step: tune the exposure threshold used to mark high exposure and retest the guardrail plan under a higher sampling rate, so you can measure false positives and latency impact. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.